The following animation demonstrates an application of PBMO for optimally designing a new groundwater remediation system at a Superfund site near Hastings, Nebraska. The site is located a half-mile southwest of Hastings in Adams County, Nebraska. From 1959 to 1985, a grain fumigant consisting primarily of carbon tetrachloride, a volatile organic compound or VOC, was used at the 22-acre grain storage facility. In 1994, presence of contaminations in the soil and groundwater was reported. Subsequent investigations confirmed that releases of fumigant in the shallow soils had contaminated the soil beneath the facility and created a plume of contaminated water approximately 4 miles long in an east-southeasterly direction from the facility. In the absence of cleanup activities, the current 4-mile-long contaminated groundwater plume would continue to be spread slowly in the east-southeasterly direction of groundwater flow at a rate of approximately 1/2 foot to 1.5 feet per day. Private wells in those areas could become contaminated and expose others to the contaminants. HGL developed a groundwater flow and transport model to simulate how this carbon tetrachloride plume would migrate over time if left unabated, and to serve as a design tool from which alternative remedial action designs could be tested. The modeling domain is 12.2 square miles, which encloses the entire known extent of the groundwater contamination. To correctly predict future groundwater concentrations with and without active remediation in this complex multi-layer hydraulic system, the model domain was discretized into just over 1 million active cells using 11 layers numbered consecutively from top to bottom. The available locations are shown as candidate extraction wells, green, and injection wells, red. In all, there were 1,105 candidate extraction and 47 injection locations. PBMO's role is to down-select from these options to the best total number, location, and pumping rate to remediate the plume. Additional constraints are to restrict the total drawdown to less than 6 feet to re-inject all the extracted water to conserve groundwater resources, and not to pull a downgradient TNT plume deeper into the lower aquifer. In all, there were 4,514 decision variables and over 2.2 million constraints. The optimal solution was identified as the least cost solution that did not violate any of the over 2.2 million constraints. PBMO downselected from 1,105 candidate extraction well locations to an optimal number of 8, and from 47 candidate injection wells down to an optimal number of 10. The PBMO solution used 2 management periods with the total system flow rate of 1,770 gallons per minute for the first 10 years, and then increasing it to 1,897 gallons per minute for the remaining 16.5 years, which was when the plume is completely remediated below the 5 parts per billion cleanup level. The following 3-dimensional animation compares the performance of the PBMO design. The multi-layered aquifer is shown, as is the initial tetrachloride plume configuration and the location of the TNT plume. The plume was allowed to migrate unabated until the year 2019, which accounts for the time to procure a remediation contractor, install the system, and begin operations. The flashing green wells indicate the location of the extraction wells, and the flashing red wells the injection locations. The PBMO design completes the cleanup of the entire carbon tetrachloride plume in 26.5 years. In summary, this PBMO application represents the most complex remedial design optimization problem ever attempted and successfully solved. The grid size for the 3-dimensional groundwater flow and transport model used in the optimization consisted of over 1 million model cells with specific hydraulic parameters that spanned over and throughout the 11 model layers. The optimization problem included a large number of decision variables and an extremely large number of constraints. PBMO effectively and robustly solved this multi-layer, multi-aquifer, complex remediation design challenge on the cloud.